welcome back to my class in Abstract Algebra. Last time we took up composition of functions and permutations. And today we will show that the set of permutations together with the operation composition of function is a group. In particular, we will show that the set G with operation composition of function is a group, where G is the set of permutations of the numbers 1, 2, 3, which we have shown last time, has 6 possible permutations. And we were able to construct 6 different functions from the set consisting of numbers 1, 2, 3 to the same set, where the elements of the set numbers 1, 2, 3 are assigned to the same numbers but in different order or different permutation. And the 6 permutations of the numbers 1, 2, 3, which we defined as function from the set with numbers 1, 2, 3 to the same set, we denoted by P1, P2, P3, P4, P5 up to P6. And P1 we define as the function from the set with numbers 1, 2, 3 to itself, the same set with numbers 1, 2, 3. And in this permutation or P1, a function from this set S, which we denote the set S, the set with numbers 1, 2, 3 to the same set S, assign each element of the set to itself. So 1 is assigned to 1, or 1 is the image of 1 under the function P1. 2 is the image of 2 under the function P1, and 3 is assigned to itself 3 under the function P1. P2 we define as the function from set S with numbers 1, 2, 3 to the same set S with the same numbers 1, 2, 3, or the same elements 1, 2, 3, but the numbers now 1, 2, 3 are assigned to the numbers in the permutation of 1, 2, 3. A different permutation of 1, 2, 3, in particular the permutation 1, 3, 2. So the second function P2 assigns 1 to 1, 2 to 3, and 3 to 2, where 1, 3, 2 is a second permutation of the numbers 1, 2, 3. P3 is also a function from set S with numbers 1, 2, 3 or with elements 1, 2, 3 to the same set 1, 2, 3. But the elements 1, 2, 3 of set S are assigned to the numbers in this permutation, third permutation of the numbers 1, 2, 3. Thus, the function P3 assigns 1 to 2, 2 to 1, and 3 to itself 3. The fourth function that is a function from set S with elements 1, 2, 3 to itself, set S with elements 1, 2, 3, assigns the numbers 1, 2, 3 to the numbers 2, 3, 1, which represents a fourth. The fourth permutation of the numbers 1, 2, 3. And P5, the function P5 assigns the numbers 1, 2, 3 to the fifth permutation of the numbers 1, 2, 3. And this fifth permutation is 3, 1, 2. Hence, the function P5 assigns 1 to 3, 2 to 1, and 3 to 2. And the last and sixth function from set S with elements 1, 2, 3 to the same set S 1, 2, 3 assigns. This last function is denoted by P6, P sub 6, and it assigns the numbers 1, 2, 3 to the numbers in the last and sixth permutation of the numbers 1, 2, 3. And this last permutation of 1, 2, 3 is is given by 3 to 1. And so this function p sub 6 assigns 1 to 3, 2 to itself, and 3 to 1. The operation composition of function is defined as by this equation. The composition of functions f and g evaluated at x is given by g of f of x, and the domain of the composition of functions f and g is the domain of function f, and the codomain of the composition of functions f and g is the codomain of function g. Now we will show that this set G consisting of the 6 permutations or 6 functions generated by the 6 permutations of the numbers 1, 2, 3 is a group under the operation composition of function. And today we will show an easier way to check if the given set G under the given binary operation is a group, rather than verifying if the set G under the given binary operation satisfies the 3 properties of a group: the associativity property, the existence of identity element, and the existence of inverse elements. We will construct a table to show that a non-empty set G together with a binary operation is a group. And for our example, we will use the set G of the permutations of the numbers 1, 2, 3 that give rise to 6 functions denoted by P1, P2, P3, P4, P5, and P6. And the operation involved here, the operation defined on set G is the composition of function. So we start by combining 2 functions at a time by composition of function. And we write the result in this table. At the topmost row, we write the 6 elements of set G. In the first column, after the first row, we write the same elements of set G in the same order that they appear in the topmost row. And in the first cell, first row and first column of this table, we write the binary operation. In this example, the composition of function denoted by circle. So we find all the possible combination, all the possible composition of 2 functions from set G. We start with P1, circle P1. We have shown last time that the composition of any 2 functions from set G is also a function from set S with elements 1, 2, 3 to the same set S with elements 1, 2, 3. So even before we find the composition of P1 and P2, we expect that P1, circle P1 is a function from set S with elements 1, 2, 3. Except that we do not know yet the images of these numbers 1, 2, 3 or these elements of set S under the composition of P1 with itself. So we start with 1, we find the image of 1 under the function P1. 1 is assigned to 1, and again we find the image of 1 under the function P1. 1 is assigned to 1. We find the image of 2 under P1. Under P1, the image of 1 is 1. Again, we find the image of 1 under the function P1. The image, we are now in the second element of S2. We find the image of 2 under the function P1. The image of 2 under P1 is 2. And again, we find the image of 2 under the function P1. 2 is again assigned to itself 2. Next, we find the image of 3 under the function P1. The image of 3 under P1 is 3. And again, we find the image of 3 under the function P1. And the image of 3 under the function P1 is again 3. But this function from set S to itself that assigns each element of set S to itself is the function P1. Thus, the composition of P1 with itself is equal to itself, P1. And we write that in the table. P1, circle P1 is P1. Next, we find the composition of P1 and P2, or we find P1 circle P2. And we expect that this composition of functions P1 and P2 is another function from set S with elements 1, 2, 3 to the same set S with elements 1, 2, 3, except that we do not know yet the images of 1, 2, 3 under the composition of functions P1 and P2. So we start by finding the image of 1 under P1, and under P1 the image of 1 under P1 is 1. And we now find the image of 1 under the function P2. Under the function P2, the image of 1 is 1. Thus, the image of 1 under the composition of functions P1 and P2 is 1. Now we find the image of 2 under P1. The image of 2 under P1 is 2. And we now find the image of 2 under the function P2. Under the function P2, the image of 2 is 3. Therefore, 2 is assigned to 3. 2 is assigned to 3 under the composition of functions P1 and P2. Now we find the image of 3 under P1. The image of 3 under the function P1 is 3. And we now find the image of 3 under the function P2. Under the function P2, the image of 3 is 2. Therefore, 3 is assigned to 2 under the composition of functions P1 and P2. But this function from set S to itself that assigns 1 to 1, 2 to 3, and 3 to 2 is exactly the function P2. Thus, the composition of P1, the functions P1 and P2 equals P2. And we write that in the table. P1 circle P2 is P2. We now find the composition of P1, the functions P1 and P3. That is, we find P1 circle P3. And this should be the composition of P1 and P3 should be another function from set S with elements 1, 2, 3. And we now find the images of these elements 1, 2, 3 under the composition of functions P1 and P3. And we start by finding the image of 1 under P1. The image of 1 under P1 is 1. And we now find the image of 1 under the function P3. Under the function P3, the image of 1 or 1 is assigned to 2. So 1 is assigned to 2 under the composition of functions P1 and P3. Now, next we find the image of 2 under P1. Under P1, the image of 2 is itself or 2. And we now find the image of 2 under the function P3. Under the function P3, the image of 2 is 1. Thus, 2 is assigned to 1 under the composition of functions P1 and P3. Finally, we find the image of 3 under P1. Under P1, the image of 3 is 3. And under P3, the image of 3 is 3. Thus, the composition of functions P1 and P3 assigns 1, 2, 3 to numbers 2, 1, 3 respectively. But by inspection, this function is the function P3. Thus, the composition of P1 and P3 or P1 circle P3, which is equal to this, is the function P3. In the same manner, you can show that, and you try to show that P1 circle P4 is P4. Composition of functions P1 and P5, or P1 circle P5 is P5. And the composition of functions P sub 1 and P sub 6 is P sub 6. P1 circle P4 is P4. P1 circle P5 is P5. And P1 circle P6 is P sub 6. Now we find the entries in this column. P1 column. We have P1 circle P1. We have shown is P1. Now we find P2 circle P1. And we expect that this composition of functions P2 and P1 is another function from set S with elements 1, 2, 3 to itself. We now find the images of these elements of S under the composition of functions P2 and P1. We find the image of 1 under P2. Under P2, the image of 1 is 1. And we now find the image of 1 under P1. The image of 1 under P1 is 1. Therefore, 1 is assigned to 1 under the composition of functions P2 and P1. Now we find the image of 2 under the function P2. Under the function P2, the image of 2 is 3. And we now find the image of 3 under the function P1. 3 under P1 is assigned to 3. The 2 is assigned to 3 under P2 circle P1. Now we find the image of 3 under P2. Under P2, the image of 3 is 2. And we find the image of 2 under P1. Under P1, the image of 2 is 2. Therefore, 3 is assigned to 2. Three is assigned to 2 under the composition of functions P2 and P1. But this function that assigns 1, 2, 3 to 1, 3, 2 respectively is the function P2. Hence, we have shown that P2 circle P1 is P2. And we write the answer in the table. P2 circle P1 is P2. Next, we find the composition of P3 and P1. Or we find P3 circle P1. And the composition of functions P3 and P1 should be another function from set S with elements 1, 2, 3 to itself. We now find the images of these elements 1, 2, 3 under P3 circle P1. We find first the image of 1 under P3. Under P3, the image of 1 or 1 is assigned to 2. And we now find the image of 2 under P1. Under P1, 2 is assigned to itself. Therefore, 1 is assigned to 2 under P3 circle P1. Next, we find the image of 2 under P3. Under P3, 2 is assigned to 1. We now find what is assigned to 1 under P1. And under P1, 1 is assigned to itself. Therefore, 2 is assigned to 1. Finally, we find the image of 3 under P3. Under P3, 3 is assigned to itself. And we now find the image of 3 under P1. Under P1, 3 is again assigned to itself. Therefore, 3 is assigned to itself by the composition of functions P3 and P1. And this composition of P3 and P1 that assigns 1, 2, 3 to 2, 1, 3 respectively is the same as the function P3. 1, 2, 3 are assigned to 2, 1, 3 respectively. Thus, we have shown that P3 circle P1 is P3. And we write the answer in the table. P3 circle P1 is P3. In the same way that we obtain the compositions of P2 and P1, P3 and P1, you can show that P4 circle P1 or composition of functions P4 and P1 is P4. The composition of functions P5 and P1 or P5 circle P1 is P5, and the composition of functions P6 and P1 or P sub 6 circle P sub 1 is P sub 6. And we write these results in the table. P4 circle P1 is P4. P5 circle P1 is P5. P6, circle P1 is P6. Now we find the rest of the entries in these vacant cells in this table using composition of functions. You now find the rest of the entries in the table. We start with the entry in this cell. This is equal to, the entry in this cell is equal to P2 circle P2, or composition of function P2 with itself. We find the images of these elements of S, 1, 2, 3 under the composition of function P2 with itself. We find the image of 1 under P2 and it's 1. Again, we find the image of 1 under P2 and again it's 1. Therefore, 1 is assigned to 1 under P2 circle P2. We find the image of 2 under P2. Under function P2, 2 is assigned to 3. We now find the image of 3 under the same function P2. And the image of 3 under P2 is 2. Therefore, 2 is assigned to 2. Now we find the image of 3 under P2. Under P2, 3 is assigned to 2. And again, we find the image of 2 under the same function P2. Under P2, 2 is assigned to 3. Therefore, 3 is assigned to 3. But this function that assigns the elements 1, 2, 3 to elements 1, 2, 3 respectively is the function P1. Function P1 assigns 1, 2, 3 to 1, 2, 3 respectively. So we write the answer in the table P2 circle P2 is P1. Now we find the entry here. The entry here is equal to P3 circle P3. We now find the composition of each function with itself. P1 circle P1 is P1. We have just shown that P2 circle P2 is P1. Now we find P3 circle P3. And it should be another function from set S with elements 1, 2, 3 to the same set S with the same elements 1, 2, 3. We find the image of 1 under P3. Under the function P3, 1 is assigned to 2. And we find the image of 2 under the same function P3. Under P3, the image of 2 is 1. Therefore, 1 is assigned to itself under the composition of P3 with itself. We find the image of 2 under the function P3. Under P3, 2 is assigned to 1. And again, we find the image of 1 under P3. Under P3, the image of 1 is 2. Thus, 2 is assigned to itself under P3 circle P3. Now we find the image of 3 under P3. Under the function P3, 3 is assigned to 3 to itself. And we again find the image of 3 under the same function P3. 3 again is assigned to 3. Therefore, 3 is assigned to 3 under the composition of function P3 with itself. And this is the function P1 that assigns 1, 2, 3 to 1, 2, 3 respectively. And we write the answer in the table. P3, circle P3. In this cell, we write P1. You can also show using the same way as we did when we find the composition of P2 with itself and composition of P3 with itself, that P4 circle P4 is P1. You can also show that P5 circle P5 is P1, and the composition of the function P6 with itself is P1. And we write these results in the table. P4, composition with itself is P1. And the composition of P5 with itself, P5 is P1. And the composition of the function P sub 6 with itself, P sub 6 is P1. Now we find the entry here. The entry here is equal to the composition of functions P2 and P3. And this composition of the functions P2 and P3 is a function from set S with elements 1, 2, 3 to the same set S with the same elements 1, 2, 3. We find the image of 1 under the function P2. Under P2, the image of 1 is 1. And we find the image of 1 under the function P3. Under P3, the image of 1 is 2. Therefore, 1 is assigned to 2 under P2 circle P3. Next, we find the image of 2 under the function P2. P2 assigns 2 to 3. And we find the image of 3 under the function P3. And P3 assigns 3 to itself. Therefore, 2 is assigned to 3. Next, we find the image of 3 under P2, and P2 assigns 3 to 2, and we find the image of 2 under P3. Under P3, 2 is assigned to 1. Thus, 3 is assigned to 1 under P2 circle P3. But this function that assigns 1, 2, 3 to 2, 3, 1 respectively is the function P4. Thus, P2 circle P3 is P4. And we write that in the table. Composition of P2 and P3 is P4. Next, we find the composition of P3 and P2, or P3 circle P2. We have shown that composition of P2 and P3 is P4. Now in this notation, P3 comes ahead of P2, and we now find what is the value of the composition of P3 and P2. But it should be a function from set S with elements 1, 2, 3 to the same set S. We start by finding the image of 1 under P3. P3 assigns 1 to 2, and we find the image of 2 under P2, and P2 assigns 2 to 3. Therefore, 1 is assigned to 3. Next, we find the image of 2 under P3. P3 assigns 2 to 1, and we find the image of 1 under P2, and P2 assigns 1 to 1. Therefore, 2 is assigned to 1 under the composition of P3 and P2. Finally, we find the image of 3 under P3 circle P2 by finding the image first of 3 under P3, and P3 assigns 3 to itself. Now we find the image of 3 under P2. P2 assigns 3 to 2. Therefore, 3 is assigned to 2 under the composition of functions P3 and P2. And this function that assigns 1, 2, 3 to 3, 1, 2 respectively is the function P sub 5. And we write the answer in the table. P3 circle P2 is P sub 5. Because P2 circle P3 is not the same as P3 circle P2, you can safely conclude here that the set of permutations P1 up to P6, P sub 6 under the composition of function is not commutative, or the set of permutations under composition of functions does not satisfy the commutative property. Next, we find composition of P2 and P4. And this should be a function from set S with elements 1, 2, 3. And we find the images of these elements of S. We start with 1. Find its image under P2. P2 assigns 1 to itself. And we find the image of 1 under P4. And P4 assigns 1 to 2. Therefore, 1 is assigned to 2 by this composition of P2 and P4. Next, we find the image of 2 under P2. P2 assigns 2 to 3. And under P4, P4 assigns 3 to 1. Therefore, 2 is assigned to 1 under the composition of functions P2 and P4. Next, we find the image of 3 under P2. P2 assigns 3 to 2. And P4 assigns 2 to 3. Therefore, 3 is assigned to itself by P2 circle P4. And by inspection of these functions, this function that assigns 1, 2, 3 to 2, 1, 3 respectively is the function P3. We write the answer in the table. P2 circle P4 is P3. Next, we find the entry in this cell. the entry in this cell is equal to the composition of P2 and P5. And it is another function from set S. We find the images of the elements of S, 1, 2, 3 under this composition of functions P2 and P5. We start with the image of 1 under P2. P2 assigns 1 to 1. And the function P5 assigns 1 to 3. Therefore, 1 is assigned to 3 under P2 circle P5. Next, we find the image of 2 under P5. Find the image of 2 under P2. P2 assigns 2 to 3. And P5 assigns 3 to 2. Therefore, 2 is assigned to itself under P2 circle P5. And we find the image of 3 under P2. P2 assigns 3 to 2. And P5 assigns 2 to 1. Thus, 3 is assigned to 1 by the composition of P2 and P5. Now, this function is the function P sub 6 that assigns 1, 2, 3 to 3 to 1 respectively. And we write the answer in the table. Composition of P2 and P5 is P sub 6. Now find the entry in this cell. The entry in this cell is equal to composition of P2 and P6. Under P2, the image of 1 is 1. Under P6, the image of 1 is 3. Therefore, 1 is assigned to 3 under P2 circle P6. P2 assigns 2 to 3. And P sub 6 assigns 3 to 1. Therefore, 2 is assigned to 1 under P2 circle P6. And P2 assigns 3 to 2. And P sub 6 assigns 2 to itself. Therefore, 3 is assigned to 2. And this is the function P sub 5. P sub 5 is the function that assigns 1, 2, 3 to the numbers 3, 1, 2 respectively. We write the answer in the table. P2 circle P6 is P sub 5. And you can complete the table, fill in the vacant cells with entries in the same manner that we find the composition of two functions in this row P2. We now have the completed table. This is the complete table that shows the composition of any two functions from the set G of permutations with elements the functions p1, p2, p3 up to p sub 6. And for your exercise, please try to show that the following compositions of functions are equal to their values. Show that composition of p3 and p4 is p6, p3 and p4 is p sub 6. And earlier I asked you to show that composition of p4 with itself is 1 and composition of p5 with itself, p5 is p1. Now the composition of p4 and with itself is not equal to p1, but instead you check that the composition of p4 with itself is p sub 5, and you did not show that composition of p5 with itself is p1 because the composition of p5, you check composition of p5 and p4 is p1. And the composition of p5 with itself is p4. The composition of function p sub 5 with itself, p sub 5 is p sub 4. It is not p1. But the composition of p5 and p4 is p1. So you make the changes in the table we had earlier. This is now the complete and the correct table. Now, how do we check if the given set G with whose elements are these functions p1 up to p6 is a group under the operation composition of functions? Simply inspect the table. If the non-empty set G is a group under the given binary operation, if the elements of the non-empty set G under the given binary operation appear exactly once in each row and in each column, then the given non-empty set G under the given binary operation is a group. The elements of G are the functions p1 up to p6, and by inspection of each row, you can see that each element, each function p1 up to p6, p sub 6, appears exactly 1 in each row. There is no row in this table where you can see a function appearing twice or more than once in any row. Also, by inspection of each column, you can see that each element, each of the functions p1 up to p6, p sub 6 appears exactly once or only one time in any column. You will not see a column in this table where a function, any of the 6 functions, appears more than once. So if that happens, if the elements of a non-empty set G, such as the set of functions p1 up to p sub 6 under the given binary operation appears exactly once in any row and in any column, then you can conclude that the non-empty set G together with the binary operation is a group. And for this example, we conclude that G under the binary operation composition of function, where G has these functions p1, p2, p3 up to p sub 6 as elements, is a group. You may want to verify the 3 properties of a group. The first property is associativity. you take the composition of any three functions and you can show that, and using the table you can show that associativity is satisfied by G under the operation composition of function. Let us take one example. Find the composition of functions P3, P2, and P5. Because composition of function is a binary operation, we can only combine two functions at a time. Therefore, we have to group two functions and combine the result with the third function. One way is to group P3 and P2. One way to find the composition of functions P3, P2, and P5 is to group P3 and P2. That means you take first the composition of functions P3 and P2 and the result you combine with P5 again by composition of functions. And from the table, P3 circle P2, P3 circle P2 is P5. And we combine it with itself, P5, under composition of function. Again, from the table, P5, circle P5, P5, circle P5 is P4. Now, to show that the associative property is satisfied, we try another grouping to find the composition of the functions P3, P2, and P5. And this time we group P2 and P5. That means we get first the composition of P2 and P5 and the result we combine with P3 under composition of function. From the table, we find P2 circle P5. P2 circle P5 is P6. We now find the composition of P3 and P6 from the table. P3 circle P6 is P4. Thus, we have shown that regardless of the grouping, the composition of the functions P3, P2, P5 is the same and is equal to P4. And this is the associative property. And you can verify the associative property for any three functions from the set G of functions P1 up to P6, P sub 6. Now, the second property of a group is the existence of identity element. And the identity element of a group has the property that if you combine it with any other element of the group, the result is that element. The existence property, the existence of identity element says that there exists an element E such that if you combine E with any element of G by the binary operation star, E star A is equal to the element. To find here the identity element of set G or the group of these functions, the set of these functions P1 up to P6 is that function such that if you take the composition of this function with any other function from the set G, the result is that function. And by inspection of the table, you can see that if P1 is combined with itself, the result is P1. If P1 is combined with P2, the result is P2. P1 is combined with P3, the result is P3. If you take the composition of P1 and P4, the result is P4. If you take the composition of P1 and P5, the result is P5. And the composition of P1 and P6 is P6. Therefore, we can say that P sub 1 is the identity element for the group G under composition of function. Conclude that the identity element for this set, for this group of permutations G under the composition of function is P1 because, or since, if you combine P1 with any other function P sub I, for I is 1 to 6, or if you take the composition of P1 and any other function P sub I, for I is 1 to 6, the result is P sub I. Now we are left to the third property left to verify is the existence of inverse elements. The third property of a group, the existence of inverse element for each of the element of the non-empty set G, states that for every A element of G, there exists an element also of G denoted by A prime, such that if you combine A with A prime by the binary operation star, the result is the identity element of the group or the non-empty set G. Now, because this set is the set of functions P1 to P sub 6, or simply the set of permutations of the numbers 1, 2, 3, under composition of function is already a group, and P sub 1 as the identity element, we are sure that each of these functions P1 up to P sub 6 has an inverse element, such that if we combine each of these functions with their inverse elements, the result is the identity element, which is the function P1 for this group of functions G under the operation composition of function. Now, to find the inverse functions or the inverse elements of each of these functions P1 up to P6, you inspect each row for the identity element. And the identity element we have shown earlier is the function P1. In row 1, we have the identity element P1 in this cell, and P1 is equal to P1 circle P1. In the second row, P1 appears in this cell, and P1 is equal to composition of P2 and P2. In the third row, P1 is in this cell, and P1 here is equal to composition of P3 with itself. the fourth row, we have the identity element P1 in this cell, and P1 is equal to composition of P4 and P5. In the fifth row, we have P1, the identity element P1 in this cell, and it's equal to composition of P5 and P4. And finally, in the last row, P1 appears in this cell, and P1 in this cell is equal to composition of P6 with itself. Because the composition of P1 with itself is equal to the identity element P1, we say that the inverse of P1 is itself, denoted by P1 prime. The composition of P2 with itself is equal to the identity element P1. We say that the inverse element of P2 is itself, and the inverse element of P2 is denoted by P2 prime. We also have the composition of P3 with itself equal to the identity element P1, and we take the inverse element of P3 equal to itself P3. The composition of the functions P4 and P5 is equal to the identity element P1. Therefore, we conclude that the inverse element of P4 is P5. And the inverse element of P4 is denoted by P prime sub 4. In the second to the last line, composition of P5 and P4 is P1. Thus, we conclude the inverse of P5 is P4. We have these results. The P prime 4, or the inverse of P4, is P5, and P prime sub 5, the inverse of P5, is P4. Thus, we can say that P sub 4 and P sub 5 are inverses of each other. The inverse of P5 is P4, and the inverse of P4 is P5. But the inverse of P1, P2, and P3 are themselves. The inverse of P1 is itself, the inverse of P2 is itself, and the inverse of P3 is itself. And the same way, the inverse of P6, because the composition of P sub 6 with itself is the identity element, the inverse of P sub 6 is itself. And the inverse of P sub 6 is denoted by P prime sub 6. Thus, the inverse of each of these functions exists, and the inverse elements are also elements of set G of functions P1 up to P6, such that if you combine the inverse of P1 with P1, the result is the identity element P1. If you combine the inverse of P4 with P4, the inverse of P4 is 5. If you combine P5 with P4, the result is the identity element. Thus, we have shown that all the three properties of a group, associativity, existence of identity element, and existence of inverse element, are satisfied by the set G of functions P1 up to P6 under the composition of functions. Therefore, we have shown that the set G together with the composition of function is a group. And as we said earlier, this is an easier way to determine if a non-empty set under the given binary operation is a group. Construct a table, and if the elements of the non-empty set G appears, if the elements of the non-empty set G appear exactly one time in any row or in any column, then that non-empty set G under the binary operation given on G is a group.